Hey guys, so here we are. We're going to go backwards. Anti-differentiation and indefinite integrals. So indefinite integrals means that there's no boundaries. That will make sense a little bit later. So let's just get going as we are. So we're going to do some warm-ups here. First, we're going to differentiate each of the following. So take the derivative, guys. F of x equals x cubed. Well, that's a power rule, right? So we get, bring down the exponent, subtract 1 from the exponent. Okay, now the next one, f of x equals 3 or x cubed minus 10. So let's differentiate. So we do our first term, that's the power rule, 3x squared. And then what do we do with the constant? Oh, the constant's 0. And let me actually write this in better notation so I know that we're taking the derivative. I'm not leaving much space for myself. There we go. Now the third one. Let's differentiate. So f prime of x equals, that's the power rule there, so bring down the exponent, subtract 1 from the exponent, and then c is a constant. But again, the derivative of a constant is always 0. What do you guys notice? We had 3 different equations, or f of x, 3 different functions. And when we took the derivative of each function, the derivative was the same for all of them. So what happens? If we were to go backwards, so in other words, if we started with this and went backwards, well, what's the only thing that's in common with each of these going backwards? It's x cubed. Now we have no idea what is on the other end. It could be nothing, it could be -10, it could be 5, it could be whatever. So what happens is when we go backwards, we always have to add this plus c at the end because we don't know if there's a constant added or subtracted at the end. This is one of the things that most people forget, and I will totally be honest. When I started going back into calculus and everything, that's the one thing I would forget. So if you ever catch me, remind me. All right, with this problem, when we do anti-differentiation, it can be written as the integral, so this is the integral symbol, of whatever function we're going backwards on. Just like we have dy over dx to tell us that we want to take the derivative. If we see this symbol, we know automatically it wants us to take what's called the integral. We want to anti-differentiate. Okay, so dx indicates that you are integrating with respect to x, but does not affect the integration process. So what you'll notice is that when we take the derivative, sometimes if we don't add that derivative symbol, you add on a dx at the end. But that just shows you we have a, sorry, I'm blanking out right now, that we actually have the derivative and we're going backwards. So when we have this 3x squared dx, this is the derivative, and what we're doing is we're going backwards because it's telling us to take the integral of it. Okay. C is called the constant of integration and must be written as a part of your answer when you are anti-differentiating, okay? Especially now when we have no boundaries, because we don't know if there's a constant there or not. So let's go over some of these rules here. Excuse me. When we are doing the power rule and we are going backwards, think about what we're doing. Going forward, we were bringing the exponent down in front and then subtracting 1 from the exponent. But since we're going backwards, what we're actually going to do is add 1 to the exponent, and we're going to divide by that number. Okay. Now, of course, n cannot be -1 because if we added 1 to it, we get to the 0, and anything to the 0 is 1. That's going to be a different case we'll talk about later. Constant rule. Okay, if k is a constant and we're taking no longer taking the derivative, we're taking the integral of k, that means to go backwards, we have kx. Okay, think of it if we went here, if we had kx and we were taking the derivative, that would just be the k, the coefficient there, right? So going backwards, if we have a constant, we're going to actually attach that x to it. Scalar multiplication. This is very nice because it helps us in the future, okay? Now, if we have k as a constant and so we have a coefficient in front of a function, we can also pull that k out, scalar multiplication. Constants may be factored out of the integral expression. Never factor out a variable, only the constant, okay, or the coefficient out front. Again, this makes it easier later, and you'll understand why in a minute. Not a minute, but maybe a couple of sections from now. We also have the summation rule. So if we are taking the integral of two functions that are added or subtracted onto each other, we can actually take the integral of each part separately and then put it together at the end. Okay, so we're going to do some examples right now. So we have the integral of x cubed dx. So this is the power rule, remember, and I'm going to take it slowly so we can get into the flow of things. So that means what we're going to do is add on to our exponent. So 3 plus 1 is 4. And we're going to divide by that new exponent, which is 4. Don't forget, because we have no boundaries here, we don't know what would be added on at the end, so we always add this plus c when we integrate. Number 5, this is the integral of a constant. What do we do to go backwards with the constant? Remember, we attach that x to it because it's in terms of x's. And then, of course, we don't know if there was something added onto it, so plus c. Okay, this one I'm going to show you how to separate it with the sum, but in the long run, if you want to go quicker and forget writing that sum, that's totally fine. Really, what we're saying here is we can take the integral of 4t dt plus the integral of 2 dt. So see how I can break it up for that summation? And now I have a power rule and a constant rule. So with the power rule, remember we add on to the exponent, divide by that exponent. Now usually we put a plus c here, right? But the truth is, all we need in the very end is that plus c. Because if we have a constant and another constant, we put it together, we still have a constant. Okay. So here we have the integral of a constant. So we have to add on the variable to it. In this case, we're in t's, so make sure you attach a t. And then at the very end, we have that plus c. So I'm just showing you this step in the long run. When you get faster and faster, you don't have to show this step. In which I don't want to show this step in number 7 because I don't want to lose room right now, okay? So if you see, we're going to have a power rule, and a constant rule. So the power rule, and again, I'm going to do the power rule out, but then I'm going to show you how to reduce it, okay? So I'm going to ignore the 2 by just keeping the 2 out front. Okay, I'm just looking at the y squared. Integral of y squared means we add on to the exponent and divide by that new exponent. So as you can see, I was totally guessing in this one that we would reduce, but as you can see, we cannot. Next one, I'm going to keep the 4 out front. Now I'm going to add 1 to the exponent. The exponent here is 1, so I'm going to add 1, I get 2. I'm going to divide by that new exponent. As you can see, what's going to happen here? We're going to reduce. But let's finish this and then reduce. Then we have the integral of a constant, which means we add on our variable. In this case, we're in y's. And then at the very end, you always have to have your plus c. So this would be a good answer and totally fine in a open-ended question, but we have to get ready for those multiple choice where it is reduced. So our final answer is 2y cubed over 3 plus 2y squared plus y plus c. Some of you will get fast quickly and be able to do that division in your head as you write it down. But for now, you might as well practice all the steps, right? All right. With number 8, just like we were doing when we took the derivative, is we wanted to rearrange it before we took our derivative to make it easier on us. So just by doing our integral, that's the same thing we're going to do. So just to remind you, x squared on the denominator means that we can bring that up and it becomes x to the negative 2. So right here, our first term here, we have 3 times x to the negative 2 minus, and this would be x to the negative 1/2. Remember, the square root is the 1/2 and it's in the denominator, so it's a negative exponent. This is dx. Now, usually, by the way, if you decide not to break it up with the summation, we usually keep a parenthesis here to show that the dx is with both terms, not just the x to the negative 1/2. Okay. All right, so power rules with each of them. We're going to keep the 3 up front. We have x. We're going to add on to that exponent. So negative 2 plus 1 is negative 1. And we're going to divide by that exponent, which is negative 1. And then we'll reduce them a little bit. Okay, guys? Now, we have minus. We have x. We're going to add 1. If we add 1 to negative 1/2, we get 1/2. Now, don't forget, we're dividing by that exponent, which is 1/2. Plus c. I'm running out of room. He didn't put much room for us. So what I'm going to do is I'm going to make an arrow and put the answer right here because I want to show you it in simplified form. So this would just be negative 3. Now what I'm going to do is put that exponent, that x to the negative 1, back into the denominator so we don't have negative exponents. Okay. Now here, we still have our minus. There's no minus and negative to make it positive. X to the 1/2 is a square root. And dividing by 1/2 is the same thing as multiplying by the reciprocal. Multiplying by the reciprocal would be 2 square root x. And then we have plus c. And that is our simplified answer for 8. All right, let's do this. Remember before when we were doing the derivative packet, lots of times when you had one term in the denominator, we were able to separate that. And that is exactly what we're going to do right now. So we have the integral of the square root of x over x squared plus 1 over x squared. Put it in parentheses, times dx. Now I'm going to move the denominators up. So I get the integral. And then this is 1/2 and negative 2. 1/2 and negative 2 is negative 3/2. Negative 1/2, negative 3/2. Then we have plus x to the negative 2, right? Because I'm going to bring that up. It makes it easier for us to be able to do our power rule. All right, so let me kind of divide this up so we know what we're focusing on. So I'm going to add 1 to the exponent. If I add 1, I still get negative 1/2. And I get to divide by that exponent. Add 1, divide by that exponent. All right, now let's simplify this. Okay, This becomes a square root in the denominator, right? Because it's negative. And we flip this because we multiply by the reciprocal. So the reciprocal would be -2. And then the x to the -1/2 is actually in the denominator, minus, because this is -1. And then this becomes in the denominator, which is 1 over x plus c. Very good. Did some power rule. Now a couple extensions onto this. Okay. We put a plus c when we integrate, but never when we differentiate, okay? Because sometimes we are given the initial condition, which makes it possible for us to actually solve for c and come up with the function. So that's what we're going to do in example 10 right now. All right, we have f prime of x equals x to the -2, x to the -3. So what we're going to do is take the integral. So we get f of x, because if I take the integral of the derivative, go back to the original function. This is the power rule. So I'm going to add on 1, I get -2, and divide by that new exponent. We have this plus c. All right, let's rearrange this so it's easier for me to use. So f of x equals -1 over 2x squared plus c. Now, this is saying when x is 1, the value equals 3/2. So what I'm going to do is now plug that in. So since we have this, I can say that 3/2 equals -1 over 2 times 1 squared plus c. And now I can solve for c. So I get 3/2 equals -1/2 plus c. So I'm going to add 1/2 to both sides, which means c is 2. Now I can indicate that the actual function, the standard function that we started out with, is -1 over 2 times 2x squared. Now instead of saying plus c, I'm going to say plus 2. Great. All right, number 11. I love number 11. This is where people kind of mess up, but remember, I'm always talking about what does it tell you. So d over dx tells you what? Well, that says take derivative. Okay. Now, what does this symbol say? This symbol says take integral. Right? We could actually do this. We could take the integral and then take the derivative. But what happens there? So inside out, right? So I'm going to go inside first. So here I'm going back to f of x. But here now, I'm going back to f prime. So what really happens? They cross each other out. They cancel. So our answer is just the 5 square root of x minus 1 over x squared. And sometimes we forget about that these two would cancel each other out. This will come up in other sections, okay? All right, some more. If we know the acceleration equation for an object, and if we are given initial conditions for the object's velocity and position, integration allows us to find the velocity and the position equations for the objects. So we're going back to our physics stuff. So remember, when we started doing this, we would start with a position and we would take the derivative to find the velocity, and then we would take the derivative again to find the acceleration. Now we can go backwards, right? We can start with the acceleration, take the integral and to find the velocity, and then take the integral again to find the position. Let's try this out. The acceleration of a particle at time t is given by a of t equals 4t minus 3, where a v of 1, which is the initial velocity, equals 6, and then the standard, so in other words, when time is 2, we know the position is 5. We're going to find both of these equations, okay? So first of all, let's take the integral of this 4t minus 3, and that would be dt in this case because we are in t's. These are power rules, right? So keep that coefficient out there, add 1, divide by that new exponent. Minus, this is the constant, so we just add that variable on, and don't forget at the very end we say plus c. All right, now we're actually going to use v of 1 equals 6. So that tells us that 6 equals, now I'm going to reduce this as I write this because this is 2t squared, but t is 1. Oh, why did I put t? Minus 3 times 1 plus c. Now, when you solve for c, we get, let's see, that would be -1, but we got to add it. So c equals 7. This means that our v of t equals 2t squared minus 3t plus 7. It's plus because it's positive. So there is our answer for velocity. We needed the velocity to find our standard, because now what we're going to do is we're going to take the integral of this 2t squared minus 3t plus 7 dt. Okay, power rules again, right? So this is 2t, add 1 to the exponent, divide by that exponent, minus 3, add 1 to the exponent, divide by that exponent. That's a constant there, so we add our variable on, plus c. Now, here is where it gets tricky. I already used c, and I said c equals 7. This is a new c. We can't keep it as just a normal c because we're already indicating that the normal c is 7. So when we do this, guys, usually what they like to do is put a subset in there. You could do the parentheses, but you don't have to. So I'm going to say c subset 2. So I know it doesn't equal 7. It's going to equal its new number. All right, we're going to use that s of 2 equals 5. So I get 5 equals 2 times 2 cubed all over 3 minus 3 times 2 squared all over 2 plus 7 times 2 plus c subset 2. All right, I know that you could do this in a calculator. You could probably do it by hand, but it's going to be a little bit longer, and I don't want this video to be too long, so I'm just going to do it for you. C subset 2 comes out to -25 thirds. So that means our standard equation is 2/3 t cubed minus 3/2 t squared plus 7t Now, because it's negative, I'm going to say minus 25 thirds. And that is our position. Number 13, this is our last one. Given that on Earth, the acceleration of an object due to gravity is approximately negative 32 feet a second squared. Now, I want to tell you the unit being feet per second squared tells you its acceleration. We did not need to have that vocabulary there because you should know by the units. Of course, negative indicates downward, and that makes sense because gravity brings it down. The equation for velocity of the object, the initial v subset 0, okay, and then again, the initial position is s subset 0. So in physics, you might have been told like, hey, this is your feet equation with standard position and standard velocity, and you didn't know where that came from, but now you will. Okay, so we have negative 32 feet per second squared, right? So if we take the integral of negative 32, and then this is in t, so dt, right? This is a constant, so the integral of a constant is negative 32, and we add that, attach that variable on and say plus c. Okay, well, we know that the initial velocity, so when t is 1, or t is 0, initial is 0, sorry, I said initial up here is 1, but it's at 1 second, right? So the initial is when the second is 0. So if I plug in 0, I get v subset 0 equals negative 32 times 0 plus c. So what does that make c? Well, c is the initial velocity. So I could say that the equation for the velocity is negative 32 t plus the initial velocity. Let's do the same thing for the standard, the position. So integral of 32 t plus v subset 0 dt. I get negative 32 t, add 1 to the exponent, divide by that exponent. V subset 0 would be a constant, so we're going to go v subset 0 t, and then plus c. And again, when t is 0, we get s subset 0. So negative 32 divided by 2, guys, is negative 16. Again, this is initial, so we have t equals 0. And then when we solve for c, we see that, and this is the second c, right? So subset 2. Got to be careful on that. So the c subset 2 is the initial position. So our position equation is negative 16 t squared plus initial velocity times t plus initial position. So those of you who've taken physics before, this should look familiar. So anytime we're using a situation that uses the Earth's gravity, you can always memorize these two. And we're done. So take your time. Remember to rearrange some of your negative exponents, your square roots, look at those denominators, but really you're practicing that power rule. Bye, guys.